My name is Andrew Weaver. I'm a cloud engineer at Walmart, and I focus on providing database services in the cloud.
And I'm Chad Helms, a Cassandra engineer at Walmart, kind of focused more primarily on helping our developers be successful with Cassandra overall.
So our goal today is just to give you an overview of Cassandra at Walmart, how we brought it in, some of the challenges we faced, some of the mistakes we made. And then we're going to kind of go into a particular use case that Chad and I spent the last few years working on in a little bit more detail. That's that dynamic data model. So we'll have time for questions at the end. So if you could just kind of hold those questions until the end, I think we'll have plenty of time to address those.
So just to get a quick show of hands, who's all shopped at Walmart.com? Okay, what about the stores? The store. Oh wow, more than I
like
thought.
I like it. Yeah, I don't think the Target guys raised their hand, but that's okay.
So a little bit about Walmart. These are just some interesting facts. Over 260 million customers are in our stores and online each week. We span 28 different countries, employ roughly 2.2 million associates around the globe. Over 11,000 retail units, so that includes Walmart stores and Sam's Clubs. And we have 12 different e-commerce websites.
We have an engineering presence in Bentonville, Arkansas. That's actually where Chad and I work from. Also here in the Bay Area, and we recently opened up an office in Reston, Virginia, and in Bangalore, India. So we've got over 35 production clusters, and that's over 500 nodes. Most of those are physical hardware, so bare metal. And we started looking at Cassandra back in the 0.7 days. This was around late 2010, early 2011. And things were they're kind of primitive back then. So there was no CQL, no transactions. Drivers were really bad. We had a lot of Hector code. So yeah, it was really bad. And there was actually a lot of different groups in Walmart. You know, we're a big organization, and there was actually a lot of different engineering groups, both in Bentonville and out here in Walmart.com that were looking at Cassandra. And there's just a lot of things happening, and it really was kind of a grassroots thing. Developers were getting it, trying it out, seeing how it worked and where they might use it.
Yeah, so you can imagine with the size and the number of engineers that we have a lot of use cases that fit Cassandra really well. In particular, right now, we're making a pretty big investment on modernizing all of our systems. So we're taking all these nightly batch processes, moving them into more of a real-time based application. And as we're doing that, we're seeing a huge uptake on Cassandra in general. So a lot of teams migrating, moving things into Cassandra. And then one thing in particular around real-time updates is Cassandra is really the only database that we've found that can really reasonably keep up with the real-time updates from our stores and clubs.
Yeah, and that's pretty big. I mean, a company our size with the resources we have, although we do try to keep things low cost, you know, we've got access to, you know, the full menu of databases and technologies out there, and we have a lot of them already implemented. So we're able to try a lot of different things. And so this one with you know, updates coming in from stores and clubs, I mean, you saw 11,500 retail units. So being able to ingest that data and make it available for reads to everybody in real time, I mean, that's a huge deal for us. And Cassandra is just the only thing that we've found that can actually do that. But it was hard. So, and I don't mean technically hard. I mean, we had challenges, and we'll go into what some of those challenges were and mistakes we made, but those are technical problems. We can solve those. I mean, politically, just getting through, you know, believe it or not, in 2011, you know, there were people who thought we should not be putting any important data in Cassandra period, right? So I had a lot of debates, a lot of discussions. They got a little heated at times, but
we even had data stacks involved in a few of them.
Yeah, and so, but everybody has their bias, right? But most of these people were genuinely concerned with worried about us losing data or not keeping data safe. And so you kind of have to recognize that, is that they're just kind of looking out for the company and for the company's information. So it took some extra work on our part to kind of put together this plan. What are you going to do about backups and recovery, and how are you going to deal with this eventual consistency? We've never had to deal with that before. If you actually think about it and go look at it, we've always had some form of eventual consistency. It's just a little different now. And non-ACID compliance, people's hairs catch on fire when you say, you're not ACID compliant. They just sort of, at least back then, they would just kind of assume, oh, it's a database. It's just like every other database. But Cassandra was different. So we had to kind of put together that plan and show it. But really, when it came down to it, we just had to be successful to prove it. And I'm really proud to say that we actually did that.
Yeah, so if there's other companies in here kind of fighting that same battle, I just word of advice, just kind of stand strong, and really kind of, you want to really show the success is in the implementation. So right, so stand strong, get it done, and prove it that it works.
Yeah. So we did make some mistakes. First off, we picked the wrong hardware. I think you'll hear that from a lot of people. Oh, this big data, so whatever's good for Hadoop must be good for Cassandra. And so we had these really huge boxes with lots of big, slow SATA disks. And we kind of made it work, just put them all in a big RAID 0, and you'd get by. But it wasn't really optimal, especially on the reads. So moving to SSDs really kind of helped that read latency come down. And then we could do leveled compaction, which really helps in some use cases where we've got a lot of overwrites on our data. Another one is batch workloads. So we actually had one instance where there was this team, they were processing a bunch of data, and so they had all this data in Hadoop, and they thought, well, wouldn't it be cool if we could just ETL that data into Cassandra and use Cassandra to do some more processing, and then load all that data back out again into Hadoop. And well, that just didn't work at all. That was a complete failure. And so sort of along with that, we do get use cases sometimes when developers come up to us and they're saying, okay, we're gonna do this and we're gonna do it on Cassandra, and so every night we're gonna ETL some data from the data warehouse or somewhere and load it in, and make it available for reads. And well, and that's like their primary use case. They just want to get this bulk data every night, and they're overwriting their data every night. And so that doesn't always work out well. You end up just compacting all the time, and the cluster just really suffers because of that.
Yeah, so speaking of use cases, I know that Andrew and I probably get 2 to 3 teams come up to us every week and ask, hey, we want to use Cassandra. Does our use case fit? A lot of times, no, it doesn't. And we'll tell them that. A lot of times their use case is kind of a small data where a relational database will suffice. And along that same vein of use cases, we get a lot that are perfect fits for Cassandra, but the teams have implemented a relational model into a Cassandra model, which we all know doesn't work.
And so one thing you kind of tend to see there is a quick way to evaluate a model that somebody gives you is if they have a ton of secondary indexes. So we've seen that a lot where like half the columns have a secondary index, and we kind of have to explain things and work through that and see, well, what queries are you really going to run, and how do we make this model perform it. Another one is tombstones. This one actually kind of bit us in the project we were working on. So you want to make sure you're using TTL to your advantage. That's a really handy feature if you can. But really, you've got to understand what your delete workload's going to be. And one thing we didn't realize is that when you update a column to null, that's actually a tombstone. And we were able to go back. That's the problem that we had, where we were updating to null and ended up having excessive tombstones. And there was a solution there. We just had to go back and sort of rework things to keep from generating all those tombstones. So there's one particular data model or particular use case that we want to talk about. This is dynamic data model. So back in 2011, that really triggered us to start looking at Cassandra. There's a lot of stuff going on in the industry. We got put onto this project. It was really a kind of a transformational greenfield type project, which is a really cool place to be. That doesn't happen a lot, but this was sort of, it was kind of a perfect storm for being able to go out and look at, this was really a lot of stuff happening in the industry. Cassandra was part of that. So we looked at a lot of stuff. We looked at HBase and Hadoop and things, and Cassandra ended up coming out on top. After we got through it and sort of got to play with everything, Cassandra was really kind of a no-brainer for us. So the problems that we had to solve, we had this handful of entities, different types of records that we were dealing with. Each one would have maybe dozens to even hundreds of attributes per entity. It was really sparse, and by that I mean record to record you would have a different set, a wildly different set of attributes. So it's very sparse attribution. New attributes are coming up regularly, and we needed full text search, so DSC with Solar really worked out for us. And then we would also have frequent intensive maintenance. So customers would be able to go in and initiate some maintenance process that would end up doing a lot of updates and have to read a lot of data.
And then non-functionally, right, we wanted one logical database where historically we've sharded our databases by country, right? So imagine all those countries that we're in, we'd have a duplicate database in that particular country. So we wanted to bring all that together in one database. And of course, the data that we were storing, we needed to be available 100% of the time. No downtime was acceptable. And it had to be fast. We're servicing, I don't even know how many tons and tons of reads throughout the company. So low latency and availability were big concerns.
Yeah, so we decided to do a dynamic data model. And this was on Thrift because that's all there was. This was before CQL. And who's actually modeled in Thrift before? Can we? Okay, so there's a few of you. You don't count. So this was in Thrift. So it looks something like this. This is sort of what the schema might look like. There's not a lot here, but so we've got this column family called stuff. And there's two columns defined here. There's a type and a user key. And then down there at the bottom, you can see this default validation class is bytes type. What that meant is you could just write whatever you wanted to in there, just bytes. Just write it however you wanted to. And that was like super cool because that's exactly what we wanted. We could just add columns on the fly in the code. And so really the schema was in the code. And we just kind of went to town, basically. And
yes, that is true. We did cache everything, so in the rows and keys at that time.
Yeah, I don't recommend caching equals all. That was bad. But I left it in there, see if anybody might catch it. And here's what a record might look like. So we got one row with one column, so a row key of foo, and this description is foo. And so that worked. Then we started getting a little bit fancy, and okay, well let's make it a little dimensional. So we would do like this. In this case, this is a language code, so we got a different description for another language. So we started adding all this stuff, and this got really complex really fast, and we had some significant serialization logic in our code, right? Everything was locked away in the code, and so it got pretty complex.
Yeah, so then anybody can guess what happened? Anybody? What came about? CQL. And then our first impression of CQL was, hey, you're breaking our dynamic model. You're killing us here. You're putting training wheels on our database that we've had a successful implementation with. But we did see the community growing towards CQL, and admittedly, it had a lot of valuable features that we wanted to take advantage of. So we got aboard.
But how to get there? So yeah, we were using Hector and everything, and so as part of this migration, we did move to the DataStax driver and CQL. But when CQL came along, it really sort of pointed out this deficiency we had, and it was we were getting into this world of schemaless, which is a very dangerous place to be, and so the application defined the schema, and so if you really wanted to know how things work, you'd have to go into the code, and so maintainability suffered because of this. So it was pretty fragile. So a small change in the code could really render all of your data unreadable. And it made, since the schema wasn't obvious, it made reading the data with something like Hadoop really hard. So we had drifted pretty far into this world of schemaless.
And then one particular instance where it really kind of bit us, is if you remember the use case we had, we need to have real-time text search, full text search on all of the entities and all the attributes, right? So we got into a huge heap of trouble. Pun intended.
That's a Java pun.
So we had all this coded up with Thrift. Everything was working. All of our unit tests, everything was successful. So we wanted to put a stress test, a load test on this data. And we quickly identified we had a huge spike in latency, long GC pauses, and the cluster was dying. And we weren't able to restart our Solar nodes. We tried clearing all the commit logs, increasing the heap to 16 gigs, and they would not start. They were running out of heap. So at that time, we were like, hey, let's get DataStax involved, called a few people. They got engaged, and they uncovered that we had literally billions of fields that were trying to be indexed in Solar. So this was an exact problem of our schemaless model and our dynamic Solar schema.
Yeah. So we kind of had like a index all the things mentality, and so that it really we really had to kind of dial that back and really look at what we wanted to do. So this is sort of what we did in CQL. This looks an awful lot what you might define in a relational model to do a dynamic database. The difference is this will actually work. We actually have a history of trying this in this type of dynamic model in a relational database, and it just doesn't perform well. So you can see here we've got this table with a partition key of ID, and then clustering columns on this context and attribute ID field. So here's kind of what some data in that table might look like. You can see that context column is what's giving us the dimensionality now. So this isn't perfect, right? So there's still that context has to be parsed and generated consistently. And in the same way, this value is just text. So you have to manage that consistently as well. But it's a lot better place to be. Queries, you can actually express meaningful queries doing slices on context and attribute ID. And now that you can actually see the schema, you can get a hint to what's actually in there.
Yeah, this was a pretty big win for our data analysts and DAs that we work with. They were able to actually look at the schema, actually run some queries, and actually see the data, whereas before you really couldn't. So this really helped them out.
Yeah, and one thing we're not really showing here is there's a lot there's more metadata to this, so that's really important when you're doing this type of work where you need to define attributes on the fly. There's a whole schema for dealing with the attributes themselves. You know, what's their data type? What are they? So that's also really critical to get right.
So we started with multiple relational databases. Remember, we started by country. So some of the results that we saw, this isn't all of them, but this is a few high points when we transitioned into Cassandra. We consolidated all those different databases into one, so we were able to, they're not completely sunsetted yet, but they're on their way out. So it used to take, and I kid you not, 3 to 6 months to add a new attribute to the system, where now we can do it in minutes, really, hours, depending on the governance process of those attributes. We did see service response times drop from 800 milliseconds to 50 milliseconds. So a huge win for our consumers of all of our services. They really appreciated that. And of course, zero downtime. We've done, 10, 12 upgrades, even refreshed the hardware completely in production, and zero downtime. So that was a huge success.
Yeah, and I mean, no joke there, actually zero downtime. It's literally never gone down in production. Also, we kind of learned Cassandra is not just for time series, right? So those golden use cases that Cassandra is a really good fit for, those are good, but there's also more use cases you can that Cassandra really works well for, and that set of use cases is actually growing as features and the product matures. Eventual consistency is a worthwhile trade-off. It really is. I mean, if you're telling me I can get always on, active database where I'm always writable, always readable in multiple data centers, and it's fast, I'm going to live with eventual consistency. It's really, most of the use cases, it's immaterial, it doesn't matter, and you just have to kind of know where it does matter and plan appropriately for it. I don't think we've run into a use case yet where we haven't been able to satisfy the requirement because of eventual consistency.
And then one common theme that you're going to hear through, which I've already heard several sessions, is the data modeling is critical. I can't express that enough to the teams that come up to us and ask for help and assistance. Your data model is so key to your application and to your cluster. If that's not correct, more than likely it's going to fail. So pay special attention to that data model.
And so CQL's expressiveness really does make modeling easier. It is a mind shift if you're coming from a relational background, and you kind of have to carry people along with that. You know, we're getting conversations all the time, and like, well, you can't join these two tables. You just can't. And they are like, well, they're stuck at that point. Like, well, what am I going to do? And then you show them like, oh, well, there's these collection types. You could use those. And sometimes, oh, okay, that solves the problem. And so it really kind of opens up the options for how you design your database, especially if you're coming from a relational background. CQL has a lot of power, and it's getting better.
And then for those use cases that require the full text search, right? Just like the data model, be intentional with your Solr schema and really put some thoughts behind that. Only index the fields that you really need indexed, and leave the other ones out. Just really put some thought behind your Solr schema in general.
Yeah, so it looks like we have ample time for questions at the end here, so. Maybe just raise
I think they have a mic.
Yes.
They're gonna.
Yeah, we'll run a mic to you.
Hello? Yeah. Hey, thank you. So I have a question. Like as you mentioned, at the beginning there are a lot of doubts about securities and safeties. So I'm wondering in your stocks if there are some certain attributes that are sensitive. How do you prevent it from being globally accessed? How do you solve those problems?
Okay, so if you're storing sensitive data, how do you protect that data?
Yeah, like the same record, same row, some attributes, some columns you want it to be globally accessed, but some columns you want to limit the access to certain users or certain groups. How do you do those?
So at a cell level, I think that level of security is not really built into Cassandra or DSE.
Yes.
As far as I know. So, I mean, obviously the features of encryption and things like that are there, but actually the access to the information and preventing unauthorized access at a cell level, that's just not there. That would be, at this point, it's up to the application to take care of that.
It's funny you asked that question. We have an actual project going on right now where we're dealing with that right now. So it's not been fully implemented yet, so I don't have any details to share.
We're still investigating some of that as well.
Okay, thank you.
Yes, down here.
Thank you for the presentation. It's really good because this is Walmart has the size and scale which we are dealing with in other places. My question is around when you look at a data model of an existing application, one of the first questions that get asked is, I have to redo the data model? You got to be kidding. And you go like, well, yeah. And what is the level of effort? And I know it is a very general question that you start, what is the methodology you adopted? That's the real question of looking at data model or models for different applications, then developing a kind of an estimated level of effort, complexity, risk. Could you shed some light on that?
Yeah, so obviously if somebody's coming to you with a data model, the first thing I say is, well, okay, thank you for the model. Now tell me about your queries, right? Because that's not documented in the relational model. I've got to know what your read and write patterns are in order to transition that into a Cassandra model. So it can be tedious, right? I mean, I've seen some massive relational models with hundreds of tables and everything. And I mean, I don't have a silver bullet. It's not, going one-to-one is almost never the right way to do it unless it's just a trivial model. But I mean, I'll tell you the data modeling class from DataStax is very helpful, and it's very methodical in how you go through and document everything and do your ERD and document your query patterns and really lay it out. And I mean, we've gotten a huge benefit from that, but it just takes the time to go in there. And to your point about, well, that, oh man, now I got to redo everything. Well, I mean, if it was working for you in the relational model, obviously, I mean, you're coming to me as a Cassandra engineer because you've got a problem to solve. So, yeah, you kind of got to change the model a lot of times.
I was also asking about the level of effort it takes, or is there a methodology you adopted or some gross numbers you could share to actually go through that?
It's case by case, honestly. It's you get some requests that come in and they're pretty simple, straightforward. They have a 1 or 5 to 10 different queries that they have to serve, and those are pretty easy, right? But then when you get into the use cases where I have lots of entities that relate to other entities, and I have all these different queries that I got to serve, that's where it's a little bit more in depth, and you're meeting with the customer several times to get it right, and working through some prototyping. So it takes some time depending on how complex the data model is.
Yeah, my question is more on the zero downtime that you mentioned, right? So can you touch a little bit on that, because I would assume like some of the models have to be rewritten. Like you might have got into some data model some kind of tables based on your query patterns and figured out, hey, this is no more the right thing, and application probably expecting that data from that data, that set of tables, and now you have to rip that into something else. So in conditions like that, which would exist almost in every solutions, how do you take care of the zero downtime part on that?
Okay, so the question is, as you're evolving the database schema, how do you achieve that zero downtime? So we've done everything in a backwards compatible manner. So we have tables that have a number. The table name has a number at the end because we've versioned that table. So we've done a lot of work where we've done this a few times actually, where we've migrated the schema. One was a wholesale thrift to CQL, but then even after we were in CQL, we determined that even in some pretty critical tables, we needed to modify the schema. And the way we've done that is to create the new table and update the application to write to both tables. So the -1 table and the new table, we'll write to both of those, and we'll do that over a period of time, and we'll migrate the data over. So we actually got kind of clever one time where we essentially would check on reads, we would check the new table to see if the data was there, and if it wasn't, we'd fall back to the old table. And that way we did this slow migration of doing these dual writes, and then you could think of it as like a read repair, right? Like, oh, well, it's not in the new table, let me read it from the old table and update and move that data into the new table. And we've done that a few times, and it's actually worked out pretty well for us. So if you have the headroom to double your writes for a period of time, it actually works out really well that way, to simply create a new table and then slowly migrate over to it. And that's how we've evolved the schema without having to take down the cluster, without having to take down the application, and it's enabled us to just run continuously.
Yeah, I think we've done that. We've done that probably 4 times in this particular use case that we talked about.
So,
yeah, the application would write to multiple versions of the table.
Mm-hmm.
I have a question about the dynamic table that you guys described.
Mm-hmm.
Could you go in just a little bit more detail into the use case of why you needed a table like that?
The particular use case, I can't get too specific, but I think the problem, so a handful of entities, right? So different kinds of things, right? And each thing may have dozens to hundreds of attributes, and then they're all very different. I'm not sure how else to describe it, but yeah, it's just this sparse attribution of information. So and this all goes into one table, right? So we basically built services around the database, and just a RESTful interface into it, and JSON in, JSON out. It just kind of talks JSON.
So we could easily add a new entity to the system without having to really change the model and new attributes.
So I'm curious about why or if you looked at maps or other collection data types, and why you chose not to use them?
Yeah, so back in that CQL table, that's not the only way to do it, to be honest. This is actually one way to do it. So to the keen observer, this really won't work in Solr, right? Because it's a CQL row, right? Like if you search, you're going to get a single CQL row back instead of all the rows, all the attributes for the ID. So what we actually do there is, this was a further optimization for Solr, where we have another table that we write to specifically for Solr, and it's writing all these attributes as a map. And so you're a little bit limited there to some degree. That's another way to do it if that works for your use case. But what that let us do is it's all in one CQL row, and so that means it's one Solr document. And we can actually put some some filtering and transformation in between there to sort of make Solr indexing work a little bit better. So like we could discard fields that we know we don't need to index. So that's like an optimization you can do there. But that actually works really well for Solr. Is just if you got a dynamic model, and we use all dynamic fields, mostly dynamic fields in Solr. So we're doing the wildcards, and that works with a map.
And actually, I think, Tim, more to your question, there's another version of this table where the value is a collection. So we can have multiple values for a particular attribute.
So did you have any situation where you have a table and then half of the data would stay in RDBMS and half of the data is going to go Cassandra, and where you are pointing to Cassandra to fetch the unstructured data, or
no, I wouldn't say we have that. I think the way we would solve that would be sort of further up in the stack at the service layer. So we're kind of big, at least Chad and I are big on microservices. So if it was coming from a relational database, that would probably be further up in the stack, and then you'd have a service that would combine those.
So we have situation where in a table we have two kind of data. One is like attribute data, which we don't know how it's going to come. There will be one product might have 10 attributes, other might have like 100. And the other data where we want to have the column level access, that somebody should be able to see only this much data, somebody should be able to see other part of the data. So we are thinking of like anything which has accessibility need, we put in the RDBMS, and rest can go into NoSQL database. Is it the right thinking, you think, or you wouldn't take that approach?
So you're splitting your data between Cassandra and a relational database.
And relational database will have only the one which we need accessibility.
So what do you mean by accessibility?
Meaning, like, we wanted to have some folks see some of the specific column, other rows would see another column, like what you addressed before.
Oh, okay. So sort of a static part of your model is in the relational, and then the dynamic part
goes into Cassandra, and then connect them with a reference.
It's just operationally a lot easier to just put it all in Cassandra.
Then how you won't be able to, and then your application level accessibility is what you're saying.
Yeah.
Okay.
We can maybe talk a little bit later after this,
sure.
More details.
Mm-hmm. Yeah, definitely.
Any other questions? In the back?
Okay, so one more question. So in this data model, you mentioned you are using context tags to save extra dimensions, and you set it as a clustering key. So my question is, if you have multiple dimension information you want to save into this context, and you want to search on a certain dimension, then in that case, when you are querying, are you performing a key lookup or are you performing a search? Because you have multiple dimensions all numbered together in this column, single column.
Right. So so we don't do Solr searches on that particular column.
So how do you query on a certain dimension, specific dimension?
So in this case, it sort of works out for us because that those dimensional, those context attributes, everything we're wrapping up in that context is provided to the service. So that's part of the lookup, part of the key lookup that you're doing. So there's kind of a couple of ways to read it. One, you're querying the data, and you know the context.
So I'll give an example. For example, if the record in the context, the text says foo equals blah, comma, and language equals FR, and you want to query find records with language equals FR, how would you query on that context column?
Yeah, I don't think we have a lot of time to address that, but basically the context is being provided at the read when the data is being queried. So we kind of know that ahead of time. But we're kind of out of time now, but we can, you can come up and we can talk about that.
Okay. Thank you.
Thank you, everybody.